Definition of differentiability at a point. Hello everyone. To begin, let's take a moment to look back at what we have already covered. In our previous sections, we reviewed the general process and the various rules used to find derivatives of functions. However, it is important to realize that these rules cannot be applied blindly. In reality, not every function possesses a derivative at every single point within its domain. There are certain instances where a derivative simply does not exist. Because of this subsection will focus on the formal criteria and the specific mathematical requirements we use to determine whether a function is differentiable at a specific point. Over the next few slides, we will move from the conceptual understanding of smoothness to the formal limit definitions and practical examples to help you master this concept. Understanding the concept. Now that we have introduced the general idea, let's move on to understanding the concept of differentiability more intuitively. First, you can think of differentiability as a measure of the smoothness of a function. When we say a graph is smooth, we mean it doesn't have any abrupt changes in direction. To put this in geometric terms, if a function is differentiable at a specific point, which we will call point C, it means that the graph of the function possesses a unique, well-defined tangent line at that exact point. In other words, there is one clear slope that describes the function's behavior at point C. However, this is not always the case. If the graph contains a sharp corner, a cusp, or a break, which we call a discontinuity, the function is not differentiable at that specific location. This is because, at these points, it is impossible to draw a single, unique tangent line. Understanding this visual intuition is crucial, as it sets the stage for the formal mathematical definition and the limit calculations we will explore in the upcoming slides. The formal definition. Now that we have discussed the geometric concept of smoothness and the idea of a unique tangent line, let us move on to the formal mathematical definition. A real-valued function f is said to be differentiable at a specific point, x equals c, if the following limit exists and results in a finite number. This is expressed as f prime of c, which equals the limit as h approaches 0 of the quantity f of c plus h, minus f of c, all divided by h. To put this into perspective, this limit represents the instantaneous rate of change of the function exactly at the point x equals c essentially. It is the mathematical way of calculating the slope of the tangent line we mentioned in the previous slide. However, it is important to note that for this limit to exist, the function must approach the same value regardless of whether h approaches 0 from the positive side or the negative side. If the values from these two directions differ, the limit does not exist, and the function is not differentiable at that point. This requirement is crucial, and it leads us directly into our next section, where we will examine the left-hand and right-hand derivatives in more detail. Left-hand and right-hand derivatives. Now that we have established the formal definition of a derivative in the previous slide, let's look at how we actually apply this in a practical setting. To determine if a function is truly differentiable at a specific point, we cannot simply look at the general limit. Instead, we must split that limit into two separate, one-sided limits. To practically check for differentiability, we split the limit into two one-sided limits. First, let's examine the right-hand derivative, which we refer to as the RHD. The right-hand derivative is the derivative calculated as we approach the point C from the right side of the graph. In this scenario, the value h is treated as a very small positive number. Mathematically, the right-hand derivative is expressed as the limit as h approaches 0 from the positive side of the fraction, f of c plus h minus f of c, all divided by h. Next, we have the left-hand derivative, or the LHD. This is the derivative calculated as we approach the point C from the left side. In this case, h is a small negative value. The formula for the left-hand derivative is written as the limit as h approaches 0 from the negative side of the fraction, f of c plus h minus f of c, all divided by h. By breaking the process down into these two one-sided limits, we can precisely analyze the behavior of the function from both directions. In the next slide, we will discuss the specific condition that must be met between these two values for a function to be considered differentiable. The condition for differentiability. Now that we have defined the left-hand and right-hand derivatives in the previous slide, let's look at the specific conditions required for a function to be considered differentiable at a point. For a function f to be differentiable at x equals c, three strict conditions must be met. First, the left-hand derivative must exist, and it must be a finite value. Second, the right-hand derivative must also exist and be finite. And third, these two values, the left-hand derivative and the right-hand derivative, must be exactly equal to one another. To put this into mathematical terms, we are stating that the limit as h approaches 0 from the negative side of the fraction f of c plus h minus f of c, all divided by h, must equal the limit as h approaches 0 from the positive side of that same fraction. Essentially, the slope of the function as you approach the point from the left must match the slope as you approach from the right. If any of these three conditions are not satisfied, for instance, if the two limits result in different numbers, or if one of the limits is infinite, then we conclude that the function is non-differentiable at x equals c. In the next slide, I will share a real-world analogy to help you visualize why this equality of slopes is so important for a function to be smooth. Real-world analogy. Now, to help you visualize the formal conditions we just discussed regarding the left and right-hand derivatives, let's use a real-world analogy. Imagine you're driving a car along a path. If the path is a smooth curve, you can turn the steering wheel gradually and continuously to follow the road. In mathematical terms, this represents a differentiable path, because at every single point, there is a clear, unique direction you are heading. However, consider a different scenario. If the path has a sudden, sharp, V-shaped turn, you would not be able to simply glide through it. Instead, you would have to stop the car completely and pivot it instantly to stay on the road. This sharp point represents a non-differentiable point. This is because, at the exact vertex of the V, there is no single, well-defined direction, or tangent line, that the car is following. The direction you were traveling from the left is fundamentally different from the direction you must take to the right. Having this geometric intuition is crucial, as it explains why the left-hand and right-hand derivatives must be equal for a function to be differentiable. Now that we understand the concept visually, let's move on to a step-by-step example to see how to calculate this mathematically. Step-by-step example. Now that we have covered the theoretical definitions and the conceptual analogy of the smooth path, let us apply these principles to a concrete example. We want to determine if the function f of x is differentiable at the point x equals 1. Notice that we are dealing with a piecewise function here. For values of x greater than or equal to 1, the function is defined as x squared. However, for values of x less than 1, the function is defined as 2x minus 1. To check for differentiability, we will follow a systematic four-step process. Step 1, we must first find the actual value of the function at our point of interest, where c equals 1. Since 1 falls into the first category, we use the expression x squared. 1 squared equals 1, so f of 1 is 1. Step 2, we calculate the right-hand derivative, or RHD. Because we are approaching x equals 1 from the right, we use the part of the function where x is greater than or equal to 1, which is x squared. We set up the limit as h approaches 0 from the right of the difference quotient. F of 1 plus h minus f of 1, all divided by h substituting our values, this becomes the limit as h approaches 0 from the right of 1 plus h squared minus 1, all over h expanding the squared term, we get 1 plus 2h plus h squared minus 1. All over h the ones cancel out, leaving us with 2h plus h squared over h by factoring out h. We simplify this to the limit of 2 plus h as h approaches 0. This gives us a right-hand derivative of 2. Step 3, now we calculate the left-hand derivative, or LHD. Since we are approaching from the left, we must use the second part of our function, which is 2x minus 1. Again, we set up the limit as h approaches 0 from the left of the difference quotient. F of 1 plus h minus f of 1, all divided by h substituting the expression, we get the limit as h approaches 0 from the left of 2 times the quantity 1 plus h minus 1, then subtracting the f of 1 value, which was 1, all divided by h simplifying the numerator, we have 2 plus 2h minus 1, all over h. This simplifies further to 2h over h. The h terms cancel out, leaving us with a left-hand derivative of 2. Step 4. Finally, we compare our results. We found that the left-hand derivative is 2 and the right-hand derivative is also 2. Since both limits exist, are finite, and are exactly equal to each other, we can conclude that the function f of x is indeed differentiable at x equals 1. This means that at this specific point, the two different pieces of the function meet smoothly, creating a unique tangent line. As we move to the next slide, keep this result in mind, as we will discuss some common pitfalls students encounter when making these determinations. Key takeaways. Now that we have worked through the formal definitions and a practical example, let's summarize the key takeaways from this section to ensure you have a solid grasp of the concept. First, remember that from a geometric perspective, differentiability requires the existence of a unique tangent line at a given point. This is the mathematical way of saying the graph must be smooth at that location. Secondly, in terms of calculation, a function is differentiable at a point, which we've called C, if and only if the left-hand derivative is equal to the right-hand derivative, and both of these values are finite. If these two one-sided limits don't match, or if they result in infinity, the derivative does not exist. Thirdly, it is important to recognize where differentiability fails. Non-differentiability occurs at sharp corners, cusps, or any points of discontinuity. Think back to our driving analogy. Anywhere the path forces an abrupt change in direction rather than a gradual curve is a point of non-differentiability. Finally, always keep in mind that the formal formula for the derivative at a point is fundamentally based on the limit of the difference quotient, which measures the instantaneous rate of change. With these core principles in mind, let's move to the final slide, where we will discuss some common mistakes students often make so that you can avoid them in your exams. Common mistakes. Now that we have covered the theory and a practical example, let's conclude by discussing some common mistakes students often make when determining differentiability. First, there is the tendency to assume that continuity implies differentiability. It is a common error to believe that as long as a function is continuous, meaning you can draw it without lifting your pen from the paper, it must be differentiable. However, this is false. A classic example is the absolute value of x. While this function is continuous at x equals 0, it forms a sharp V-shape. As we discussed in our car analogy earlier, that sharp corner means there is no unique tangent line, making it non-differentiable at that specific point. Second, do not ignore the requirement that the limit must be finite. In some cases, you might find that the left-hand derivative and the right-hand derivative are equal, but both are infinite. This typically occurs when the graph has a vertical tangent. Even though the two sides match, because the result is not a finite number, the function is still considered non-differentiable at that point. Finally, be mindful of your function selection when dealing with piecewise functions. Referring back to the step-by-step example we just completed, it is crucial to use the correct expression for each side. Always ensure you use the piece of the function defined for x less than c to find the left-hand derivative, and the piece defined for x greater than c to find the right-hand derivative. Using the wrong expression is a frequent oversight that will lead to an incorrect result.